continue on with our lecture. Okay, so when we last left off, we discussed many reactions of nitriles. One reaction that stood out is the reaction of nitriles with Grignard reagents to prepare asymmetrically substituted ketones. So we noted that in previous examples, for example, the problem that we looked at just before our break in our lecture session, where Grignards will add selectively into nitriles, and after aqueous workup, we're able to isolate the corresponding ketone. So we can use this reaction of nitriles in planning our synthesis of various ketones. So what I'd like us to do is to take a look at the following asymmetrically substituted ketone, and I'd like us to try to propose a synthesis for this ketone from a nitrile starting material. Okay. So retrosynthetically, we're trying to trace back this ketone into a nitrile starting material. So let's take about 3 to 4 minutes, and I'd like us to try to draw the structure of our starting materials and to draw the forward reaction to complete this synthesis. Note, there are at least 2 possible solutions using the method that we just learned in class today. So let's work through this example, and if there are any questions I can address, don't be shy to ask them in the chat or verbally, and I'd like students to share their responses as either a photo in the chat or annotated directly onto the class whiteboard. So let's work through this example, and I'd like students to propose a synthesis of the following ketone from a nitrile starting material. So let's keep working through this example, and I'd like you to share your responses in the chat or verbally. So does anyone have a proposal? Would anyone like to share their proposed synthesis of the following ketone from a nitrile? What do our nitrile starting materials look like for this reaction? And okay, we have one student thinking, okay, I'll break this bond, and that gives us ethyl magnesium bromide and the following nitrile. Okay, that's one disconnection. What's another disconnection that we can think about retrosynthetically? So breaking our other carbon-carbon bond would give us the 2 starting materials of, in this case, isopropyl magnesium bromide and a propanoic acid derived nitrile. Perfect. Okay, so in a forward sense, if we wanted to prepare this ketone, all we would have to do is take our nitrile, react it with isopropyl magnesium bromide, and then treat with water. That in turn would give us our desired ethyl isopropyl ketone. Does this example make sense? Okay, let's keep going then. And let's talk about some common reactions of carboxylic acids. So carboxylic acids can transfer a proton to a base to give anions, which are great nucleophiles in SN2 reactions. Similar to ketones, carboxylic acids undergo addition of nucleophiles to the carbonyl group. Finally, carboxylic acids can undergo alpha substitution reactions. We'll talk more about those reactions in chapter 22. Okay, so there are a range of ways that we can derivatize carboxylic acids. Let's talk a little bit and let's really draw a parallel between carboxylic acids and nitriles in that nitriles and carboxylic acids both contain an electrophilic carbon atom and have the same oxidation state. Thus, carboxylic acids, nitriles, and esters are often viewed as synthetic equivalents. And whether or not you decide to plan your synthesis going through a carboxylic acid or nitrile really depends on the exact pattern of reactivity you need. Because although they have a similar oxidation state, as we've seen, for example, with reactions with Grignard reagents, they have different chemoselectivity patterns. Okay, so we've seen that we can hydrolyze a nitrile to make a carboxylic acid. Let's talk about a reverse reaction where we take a amide and we can dehydrate it to make a nitrile. So if you have a primary amide, treatment with thionyl chloride or phosphorus oxychloride yields the corresponding nitrile. This is a useful method to prepare nitriles in that this dehydration step is unlikely to, you're less likely to see the kind of elimination or other issues with hindered substrates. So for example, if you tried to prepare this nitrile from the corresponding alkyl halide, you'd have a little bit of difficulty. It's a secondary substrate, it's a little bit hindered. If you go from the corresponding amide, however, this dehydration occurs readily, even on hindered substrates. Now, it's important to note, and this is really important to help guide our discussion for the reactivity of amides. It's important to note that amides are more nucleophilic at oxygen compared to nitrogen. If you look at the resonance structure, you can begin to see why, in that nitrogen can more readily accommodate a positive charge. And so this minor resonance structure where the lone pair of nitrogen is tied up in this pi system and oxygen is extremely electron rich is a pretty reasonable description and depiction of how the electron density is arranged for this amide. Generally, amides prefer to react at oxygen rather than nitrogen. Does that point make sense to everyone? This is important before we look at this next mechanism. Does this idea make sense? Okay, so in this case, looking at the mechanism for dehydration of an amide to yield a nitrile, In the first step, oxygen attacks your electrophilic sulfur atom of thionyl chloride. We then kick out chloride, and we've now activated our oxygen atom as a leaving group because we now have this chlorosulfonyl group. From here, base can pull off a proton. And finally, a second equivalent of base pulls off our final proton, promoting elimination and loss of our leaving group. This cleanly gives us our desired nitrile. And the beautiful thing about this thionyl chloride mediated dehydration is that our leaving group decomposes. And as a result, it's very difficult for the reverse reaction to occur. It's functionally impossible for you to see substantial reverse reaction. So this is a useful method to prepare nitriles from amides, because as we've seen, amides have different patterns of reactivity compared to nitriles. Does this make sense? Do you see how this leaving group decomposes, how you get SO2 gas as a byproduct? That's part of what makes thionyl chloride such a great activating agent, in that it activates your alcohol as a leaving group, and then once your leaving group leaves, it decomposes. Did that answer your question? Perfect. Okay. Now, we've seen, just like carbonyls, nitriles are polarized and they can react with nucleophiles at the nitrile carbon. We've seen this with Grignard reagents time and time again as a useful method to prepare disubstituted ketones. Now, what we're next going to talk about is this idea that nitriles and other carbonyl groups can undergo reaction with other nucleophiles and undergo what are known as substitution reactions. We're going to talk a lot about these reactions next chapter. As a general rule, carbonyl substitution reactions, similar to nucleophilic substitution reactions, depend on the nucleophile and your leaving group. If your nucleophile is a strong nucleophile and the leaving group is a good leaving group, then these carbonyl substitution reactions favor the product. So we can make a bit of a hierarchy of reactivity, where if we look at our acyl chlorides, our anhydrides, thioesters, esters, and amides, we see generally it's quite easy to convert our more reactive acyl group derivatives into less reactive acyl group derivatives. If we think about chloride, acetate, thiolate, alkoxy groups, and amides, what we notice almost immediately is that your most reactive acyl group derivatives, thinking about chloride and acetate, so your acyl chlorides and anhydrides, what do we notice about these leaving groups? Are these leaving groups good or bad leaving groups? Are these leaving groups good or bad leaving groups in general? Great leaving groups. We see consensus among that. So even though we haven't seen all of these acyl group derivatives, we can get a sense of their relative reactivity by looking at their leaving groups and looking at whether your leaving group is a good, bad, or just a better leaving group than your nucleophile. Does this idea of acyl group reactivity and leaving group strength make sense to everyone? Okay, perfect. So, just to expand on this discussion, carbonyl substitution reactions, similar to nucleophilic substitution reactions, depend on the nucleophile and leaving group. If the nucleophile is a strong nucleophile and the leaving group is a good leaving group, this equilibrium favors the product. So, as we saw, if we have an acyl halide and if we have an anhydride, these are great leaving groups. Halides, acetate, wonderful leaving groups. If we have an ester, a carboxylic acid, an amide, that's a little more difficult. These aren't the best leaving groups. These are pretty good nucleophiles. Does this recap make sense to everyone? And does that help us start to rationalize why some of these reactions work? Is everyone starting to see why some of these reactions that we've looked at, for example, preparation of carboxylic acids via hydrolysis, when we hydrolyze an amide, does everyone start to see why some of these reactions may require changes in conditions? While reactions when we have an anhydride or an acyl chloride, those occur quite readily. Does this relationship between reactivity and leaving group capability make sense to everyone? Okay, now we looked at amide hydrolysis, right? This is one case where we're going from a relatively stable amide to a slightly less stable carboxylic acid. And when we look at this reaction, the first question is, why does this work? Well, hydrolysis is functionally a nucleophilic acyl substitution. We're taking an amide and converting it to a carboxylic acid using water as our nucleophile. Now, you may say to yourself, wait, this amide, that doesn't look like a great leaving group. That's correct. However, our real leaving group is not the amide anion. It is ammonia. And if we look and we compare ammonia to an ammonium salt, and we look at these pKa values, what we notice immediately is that after protonation, when we protonate our leaving group, so protonation of the leaving group activates the leaving group. So, especially when you're trying to hydrolyze an amide, where you don't want to kick out an equivalent of amide anion, protonation of your leaving group converts the leaving group into a much better leaving group and a much less basic and a much less nucleophilic species. So this is why acid catalyzed hydrolysis of amides works. We're using an excess of water, so we always have our nucleophilic species floating around, and we've activated our leaving group via protonation. We've seen this textbook intermediate, and we'd all agree that if we compare these leaving groups, what's a better leaving group? Ammonia or hydroxide? What's a better leaving group? Just in general, what's a better leaving group? Looking at this table relating pK, nucleophilicity, and leaving group capability. What's the better leaving group? Ammonia or hydroxide? So ammonia is a much better leaving group than hydroxide. By the same token, when we look at something like this, now what's a better leaving group? Water or amide anion? What's a better leaving group? Water or this amide anion? Water, right? So it's really important in your mechanisms you draw out these proton transfer steps appropriately, because protonation or deprotonation heavily affects the ability of a group to leave. And by the same token, it affects whether or not a given group is a good nucleophile or a terrible nucleophile. Does that make sense? Does this idea of protonation and leaving group activation make sense to everyone? We've been using this idea throughout this chapter and previous chapters. I just want to make this explicit because you'll see a lot of reactions work better under acidic conditions. And that's partially because we are activating our leaving group via protonation. Okay, so just to summarize, there are two main ways that we could get this hydrolysis to go. We can either enhance your nucleophiles under basic conditions or enhance our electrophile under acidic conditions. In both cases, we are tuning our nucleophile strength and our leaving group capability by utilizing acidic or basic conditions. So we have another nitrile hydrolysis mechanism that you can do for practice at home. One thing I want to touch on before we go, and what I want us to sort of apply what we've learned in terms of drawing mechanisms and thinking about a logical mechanism for these carbonyl substitution reactions, is I'd like us to think about this amide hydrolysis mechanism, except this time we're working under basic conditions. So sodium hydroxide with a little bit of water present for good measure. And then in the second step, we quench with an excess of water. So let's work through this example together as a class. And I want us to think, okay, what is our nucleophile? What's the first thing that's going to happen under basic conditions? And then how do we activate our leaving group? How do we prepare our leaving group for displacement? Okay, so we're under basic conditions. So the first thing I'm going to ask everyone for this mechanism is, do we start with a protonation step? If we're under basic conditions, sodium hydroxide, are we able to protonate our amide? No way. I see everyone typing in the chat, no, that's not going to work. Okay, so now we have our nucleophile, which is hydroxide. Do we have an electrophile? Do we have an electrophile that we can attack? Is there an electrophile that we can go after? The amide carbonyl carbon. Yep. Okay. Now, we're going to make a tetrahedral intermediate, and we're going to notice our first problem. It's not a problem that can't be solved, but it's a first problem that we need to acknowledge. Okay, right now, as drawn, if this tetrahedral intermediate collapses, what leaving group is better? Hydroxide or amide? What's our better leaving group right now? Hydroxide, right? So as of right now, this is an equilibrium process and we get a non-productive pathway. Okay, so how do we tilt the odds in our favor? How do we prep our amine as a leaving group? How can we prep our amine as a leaving group? Or you can also say, how do we make hydroxide a worse leaving group? So we noted that protonation can activate a leaving group and deprotonation deactivates a leaving group. So what can we do to this amide to set this up? What can we do to our amide? If we wanted to activate this amine as a leaving group, what can we do? Protonate it, yeah, for sure. So we can do a proton transfer where we pull off a proton from our alcohol and we protonate our amine. Now, what I would say is you're probably not going to get very much of this species because the amine, or in this case, your ammonium salt is pretty acidic. And you're likely going to see some proton transfer. From here now, we can kick out our activated leaving group, and that gives us our desired carboxylate salt. One other way that the book sometimes draws this mechanism is that even though this amide is not the best leaving group, they just show you kick out your amide, you have this carboxylic acid, and then your amide deprotonates it. And that gives you the carboxylate salt as well. I personally, the second mechanism is fine, but I feel like activating your leaving group before you kick it out is preferable. It's generally noted that this amide hydrolysis under basic conditions requires generally pretty high temperatures and pretty concentrated samples of sodium hydroxide in order for this reaction to proceed efficiently. And that's partially because in either case, you're kicking out a pretty recalcitrant leaving group. Does this mechanism make sense to everyone? And does this idea of leaving group capability and the ease that these carbonyl substitution reactions occur, does this idea make sense to everyone? Does this help explain why it's often a little bit difficult to hydrolyze an amide under basic conditions directly? Because you're kicking out this pretty terrible leaving group. Any other questions on this example that we've worked on together? Okay. So we've finished up chapter 20. So this is a good time for us to archive this recording.